Welcome, ladies and gentlemen. Today we are going to finish the story of developing a rotational equivalent for every significant linear quantity. Right? So we've gone from linear velocity to angular velocity, from linear acceleration to angular acceleration, from force to torque, from kinetic energy to rotational kinetic energy, and so what's left, as we've discussed already, is momentum. So we're going to develop today the concept of angular momentum. Let's get started. Angular momentum has tons of practical applications. But before we do so, let's develop the definition of angular momentum mathematically. If you look on the screen, you see two examples. We'll focus on the one on the left first. We have an object of mass m, a point mass, okay, and it has a certain linear momentum. So we have an object that has a linear momentum that's in the xy plane only. I know that's kind of hard to see, but basically this motion here is happening in the xy plane, right? So it's flat on the paper, whereas the z-axis is coming out at it. So it turns out that we're going to define angular momentum with respect to a point, okay? And that point in this case is going to be the origin. We'll call that P. Okay, so in other words, that's the first thing to recognize, is that angular momentum is actually defined as around a point rather than around an axis. We've been talking about rotation with respect to an axis. And in this case, we're going to define angular momentum is always going to be defined with respect to a point, not a whole axis. Okay, so the definition of angular momentum is going to depend on linear momentum and how far you are from that point. Okay, so the definition of angular momentum is as follows. Okay, we use the letter L. It's a vector, and it's equal to r, okay, which is our position vector, r, and we're going to label it that way, okay. It's the cross product of r and the linear momentum, which is p, okay. So it looks like this in color-coded fashion. It's a cross product. It produces a vector itself, right? Remember, the product of a vector is a vector. And so if you do the right-hand rule here, I would encourage you to stop right now and do the right-hand rule and see which way the angular momentum would point. Hopefully you'll get this result, which is that the angular momentum comes out at you, okay, out of the plane of the paper. So we're going to define angular momentum as a cross product of r and p, okay, the position vector and the linear momentum. Let's look at a different example. You'll see an object that's moving in the xy plane. So notice that I'm going to label the axes a little bit differently here. I'm going to label this x, this y, and this z. Okay, so that this circular motion, okay, so this is an object now that's moving in a circle, and the circular motion is happening in this plane here. Okay, so it's all on the xy plane, so the x is coming out at us. All right, so if we look at that circular motion, we can develop another expression for angular momentum that will be very useful to us. So again, apply the right-hand rule here to determine which way the angular momentum will be for the object of mass m, okay, with respect to the origin, which is point P. Okay, so again, see if you can apply the right-hand rule to see which way the angular momentum is. Hopefully you'll get an expression that has your thumb pointing upward, right, parallel to the z-axis. Let me label that. Okay, so you should have angular momentum that way, like so. And now let me develop that useful expression. It's another version of the angular momentum expression. I added in a few details. I'm going to work with that r cross p. I'm going to substitute in a few things here. Okay, so remember the cross product is the magnitude of the vectors, right? So we have magnitude r, magnitude mv for linear momentum, and then the sine of the angle between them. Okay, hopefully you see in this case, although it doesn't look, because we're going from 2 to 3 dimensions, but that's a right angle there between the position vector and the momentum, right? Because when you're moving in a circle, the velocity is always tangent to the circle at that point. So the sine of 90 is 1, so we get this, RMV. Okay. Remember additionally that v is related to the angular velocity in the following way. So we can make that substitution. Now we get Rm r omega. And we get a new expression that looks like this, mr squared omega. But remember that this expression here, does that look familiar? That's the moment of inertia of a point mass, right? So this is actually I omega. So we get another expression for the angular momentum of an object. It shows us that the angular momentum is parallel to the angular velocity. Okay? And that'll be very useful to us. Let's look at some practical applications of angular momentum. Okay? And again, this is really going to be supplemented by expressions in class. If you look at the scenario on the left, you have a cart of books. You might see the scenario at the end of the school year when teachers are getting their textbooks back to the pickup areas. And those carts can have a lot of momentum even though they're not moving fast, right? If you were so unfortunate as to be in its path, you would find that you would need a lot of effort, a lot of impulse, right? Impulses change momentum. You would need to deliver a lot of impulse, a lot of force over a long period of time to cause the path of that cart to safely diverge from running into you. Okay, well, it turns out that angular momentum has that same sort of thing. When you get something spinning, it develops angular momentum, and then it becomes difficult to change that direction of the angular momentum without a lot of effort. Let's look at bicycle wheels. Okay, you've noticed that when you sit on a bike and you're not moving, you just tip right over. But when you're rolling and those wheels acquire angular momentum, it now becomes possible to balance on a bike. So let's look at that. Let's just say that these wheels are going to rotate this way, okay, like so. Right? So if you do the right-hand rule, remember that we know now that angular momentum is parallel to angular velocity. Right? So we can do angular velocity here by just curling our fingers toward us, out toward us, and we are going to get an angular momentum that is this way. Right? Let me use the arrow. Okay, the angular momentum is basically to the left, right? To the left of these wheels. Okay? And so what that means is it takes effort, and you're going to be able to see this in class. It actually, when that wheel is spinning, it actually takes effort to tip the axis of the wheel. Okay, so the axis of the wheel runs this way. For you to tip that actually takes effort now. In other words, that lends a stability to the bicycle wheel to want to maintain that horizontal direction of angular momentum. Just like the cart of books wants to maintain its direction of motion, in our case, straight up. And that's what allows your bike to balance. The same thing goes for a spiral. When you're throwing a football in a spiral, let's say that we'll just pick a direction here. Okay, so the axis of spin is kind of along there, right? And let's say that it's spinning. I'm just going to pick a direction that way, right? Okay, that means that the angular momentum is coming out of the page this way, like this, right? Okay, and that lends a stability to the ball. Now, for that ball to change direction, it's going to take an effort. So that's what allows the ball to be stable in the air, because you have an angular momentum that now becomes difficult to change. So that's some of the practical side of angular momentum, and again, you're going to see a lot more examples of these in class. Let's look at a few other slices of angular momentum. Believe it or not, an object moving linearly also can be considered to have angular momentum because it's moving about the point. Okay? Imagine if you were an observer at point P, okay, and you watched this ball of mass m move past you, okay? I think you would see that you would have to rotate with the ball in order to keep up with it, right? So this is you, the observer here, right? And if this ball moved across the screen like this, right, you would have to turn to keep up with it, right? You'd have to turn to keep up with it. So in that way, an object moving linearly can be seen to have angular momentum. It's sort of, since it's requiring you to turn, right, there's a turniness, if you will, to the motion, even though you wouldn't have thought about that. But it all has to do with the fact that it's in relation to that point P. So I'm gonna pause here and fill some things in so you can see what the angular momentum looks like at this point. Okay. Okay. You see, I drew the position vector and I drew the linear momentum vector. Okay. The cross product in this case would be RMV sine theta, where theta is this angle here. Okay. Now, hopefully you'll see that this term here, right, is, if we imagine a triangle here, right, if there's a triangle here, like so, this distance here is that sine theta of that triangle. Okay. Let's imagine now that the ball is at some later point, right? Let's say it moves to here. Okay. So now we have to draw a new position vector. I didn't state this, but we're going to say that the momentum is the same. Okay, the momentum hasn't changed, moving at some constant velocity. So if we now draw that, you're going to see that the position vector has changed, right? The linear momentum is the same, okay? And hopefully you can see now that that angle has changed. This is a new angle, right? It's a bigger angle, okay? But there's a smaller r. So it turns out that in this new triangle that you have, right, in this new triangle here, this side is still the same. So what you get is that, yes, an object moving in a straight line does have an angular momentum about a point, but that angular momentum is constant. In other words, this here is r sine theta, right? So if we want to call it, and that's not going to change, right? Regardless of the position of the object, that's going to be some constant distance, call it L. All right, so if you come over here and rearrange this and you write mv r sine theta, we can see that the angular momentum of an object moving in a straight line with respect to a point is some constant value mvl, where L is that perpendicular distance. Okay, so it's surprising to students to see that an object moving in a straight line can have angular momentum, so I wanted to develop this for you so you can see that. Okay, let's move on to a few more topics. Angular momentum can be found in two varieties. It can be found in the spin variety and the orbital variety. Practical example is the Earth. Okay, so you see the Earth here moving around the sun. You know that the Earth spins as well as revolves, right? So the angular momentum of spin, right, would be in this along the axis, or tilted axis, right, because the Earth's tilted. So that would be L spin, okay? But then there's another angular momentum that we get from revolving around the sun, okay, and that's going to be straight up like that, and that's the orbital angular momentum, okay, L orbital. So you have sometimes you have two types of angular momentum to consider. Another less obvious situation of this is if you go to the right, you see this pendulum, which is basically just a bob attached to a rigid rod, okay. It turns out that this bob also has two types of angular momentum, right? It's got the angular momentum of moving about a point, right? So with respect to this point, it has angular momentum. But believe it or not, if you think about it, I think you can see that as it goes through that arc, the bob also spins. So there's two types of angular momentum to consider here. You have an online homework problem that's like that. Okay, the last thing we want to talk about is the conservation of angular momentum. Just like we have the conservation of linear momentum, so we also have the conservation of angular momentum. And I want to develop that for you as a wrap-up to today's lesson. On the left, I've substituted force for the derivative of momentum, right, which is Newton's second law of his way. On the right, I'm actually going to take the derivative of that angular momentum equation. Okay, and on the right side, I'm now going to apply the product rule. So let me write that out. All right, you see the product rule applied to the right side, okay? And then I substituted for dr dt, I substituted v, okay? Now, hopefully you'll recognize that these two are parallel, right? The direction of velocity and direction of momentum is the same. So, and the cross product of two parallel vectors is 0, right? So this comes out to 0, and this whole expression then is r cross dv dt, but hey, wait a minute, doesn't this look exactly like what we have on the left side, right? And so what we can conclude from that is that torque is equal to dl dt. That's the exact equivalent of Newton's second law of his way, which was this, okay? And remember that when the external force is 0, right, then we have linear momentum conservation. We can see that torque as well. When there is no net torque, we're going to have angular momentum conservation. And we're going to be able to apply that to lots of problem solving as well as to explaining lots of natural phenomena that have angular momentum as part of it. All right. Thank you for paying attention, and we'll see you in class.